Good afternoon, and thank you for joining us. So why did we think it was important to give a presentation on our top 5 milling technologies? As products and technologies become more advanced in today's markets, the need for materials with specific properties for special applications becomes more important. With the range of requirements being so broad, it's not practical to think that one type of milling technology will satisfy everyone's needs. I will give you an overview of some of the specific milling technologies offered by Hosokawa and used in industrial applications today. Many of our customers already know what milling equipment best suits their application requirements, but we also find that many customers only know the material characteristics they want, but are unfamiliar with the specific size reduction technology they may require, or they're unaware of the total capabilities of some process milling systems. The most important aspect of selecting a size reduction technology is to know some basic information about the product you want to process. It's important to note that based on product characteristics, only certain milling technologies may be suitable for a given application. Starting a project understanding these basic requirements will result in an economical and trouble-free milling system solution. Let's look at the effect of feed size on mill performance. Larger feed material means more residence time in the mill, and larger equipment will be required for a given production capacity. Feed size affects feeding methods and feeder selection. For example, air conveying a large high bulk density feed to a mill may not be possible. Knowing the characteristics of your feed material is important. Bulk density affects flowability of the product. Feed rate and accuracy can be affected. Light density materials may flood past the feeder, affecting feeding accuracy and mill performance. Bulk density will also affect the sizing of hoppers and finished packaging. Light bulk density material will affect grinding efficiency, as lighter materials are more difficult to keep in the grinding zone of the mill. Cohesive and sticky products may build up on mill internals and upset airflow and increase pressure drop across the mill. Systems may require the use of high velocity air to keep mill internals clean. Conditioned air for temperature and humidity control may also be required. Low melt point materials are sensitive to high energy input. Heat-sensitive products may require cooling in order to efficiently process them. Hygroscopic materials absorb moisture, causing buildup and plugging, and may require dehumidified air for processing. On the other hand, products containing moisture may allow for the high energy processing. The moisture in the product will absorb the heat of grinding, providing cooling in the process. Material hardness may lead to high component wear and increased maintenance, minimizing the selection of equipment for abrasive applications. Special wear protection of mill components may need to be considered. Here we show an ACM with all ceramic internal components. High energy input can lead to the generation of too many fines when processing fireable materials. Low energy processing may have to be employed when handling these types of materials. Impact force tends to produce sharp angular particles. Compression and shear forces tend to produce more rounded particles. High aspect ratio materials are destroyed by certain size reduction techniques. You can see that material characteristics play a very large role in machine selection and design. There are 4 basic techniques utilized in size reduction equipment for the purpose of dry particle size reduction. They include particle size reduction through the processes of shearing, attrition, compression, and impact. In some cases, a combination of these may be found in any one mill type. Milling using shear forces works when particles are stressed between 2 surfaces that are moving in opposite directions. An example would be the operation of a ball mill, where particles experience shear forces as they are stressed between the media, which is constantly in motion within the mill. Compression milling can be accomplished in 2 ways. The first would be the compression of a particle between 2 solid surfaces. An example would be the size reduction that takes place in roller mills. The second way would be the compression of a particle between grinding media. An example would be the way a horizontal ball mill functions. The principle of compression and shear forces is employed in many types of size reduction equipment. These principles are best used to produce materials with narrow particle size distributions with a limited generation of fine particles. Impact is defined as a solid object moving at high velocity coming into contact with a stationary particle. Impact milling can be accomplished in two ways. The first way is to use a moving hammer or impact element to strike and fracture a particle into smaller pieces as shown here on the left side of this slide. As an example, all hammer mills work in this way. The second way is to use a motive force to accelerate the particles into each other for particle-on-particle impact and fracture. An example of this would be jet milling technology, where compressed gas is used to provide the force needed to accelerate the particles to collide with each other. Impact is used to achieve the highest fineness possible in these types of machines. Most hard, crystalline, and amorphous particles react well to impact for the purpose of size reduction. I chose to discuss these 5 types of milling technologies as they cover more than 90% of size reduction applications in the major chemical, food, pharmaceutical, cosmetics, and minerals industries. Each of these technologies can be supplied for a variety of different applications. These mills are most always supplied as part of a complete size reduction system. We will start with the subject of hammer mills. Hosokawa manufactures the Mikro-Pulverizer hammer and screen mill and the Mikro UMP Universal Mill, a food and pharmaceutical grade milling system. The Mikro-Pulverizer can be used for pre-grinding, deagglomeration, and medium to fine size reduction. This type of hammer mill provides excellent top size control and particle size distribution control. These mills provided with knife or bar hammers can produce coarse and granular end products, but the mill is primarily used for finer grinding when the desired particle top size is in the range of 50 to 75 microns. A wide range of particle size distributions with defined top sizes can be produced with the Mikro-Pulverizer. Rotor speed, screen configuration, and the type of grinding elements provide for flexibility in producing many different end products. This hammer mill design consists of a rotor assembly with hammers that rotate inside a cylindrical housing. The top of the housing contains a multiple deflector liner, which you can see better here in the color insert at the top of the slide. Particles are accelerated into the liner by the impact force of the hammer. The impact breaks the particles into smaller pieces, and the liner slows their peripheral velocity and deflects them back into the hammer path for further size reduction. The bottom portion of the housing contains a screen as seen in the color insert at the bottom of the slide. The screen is used to control the size of the particles exiting the mill. Various screen types and hole sizes are used to change the final product size. Here you see the basic rotor assembly with impact hammers. At top rotor speed, the impact hammers travel at over 100 meters per second, or close to 20,000 feet per minute. As an example, a hammer in this type of mill traveling at top speed could cover the length of a football field in 1 second. This high energy impact produces a finished product with a high degree of fine material. The incorporation of a screen allows the Mikro-Pulverizer to produce sharper particle size distributions with a defined top size. The Mikro-Pulverizer product line consists of 8 model sizes from 1 to 350 horsepower. All models are customizable with a wide variety of components and materials of construction to meet many application requirements. These machines are economical to operate and can be incorporated into simple systems that are easy to operate and maintain. Our Mikro UMP Universal Milling System is the next generation of the Mikro-Pulverizer. It is designed specifically for use in pharmaceutical, food, and fine chemical industries where the ease of cleaning and sanitary designs are required. Most models are available with either of 4 different rotor options: hammers, pins, knives, or attrition discs. There are 5 sizes available ranging from laboratory to production scale models. Controlling particle size and particle size distribution can be accomplished in the Mikro-Pulverizer by employing a variety of different screen types and hammer designs. The sizes of the perforations and slots come in many dimensions. round-hole screens produce the finest grinds, but herringbone and cross-slot screens are employed to process sticky or fibrous materials. There are basically three types of hammer designs: the Stirrup or LFS hammer, the swing bar hammer, and the rigid bar hammer. The Stirrup hammer has the most surface area and is used at high speeds to produce the finest particle sizes. The swing bar hammer is used on materials that do not respond well to impact. Fibrous materials that need to be cut or shredded work well with these types of hammers. The rigid bar hammer is used for granular and coarse size reduction applications, and for producing narrow particle size distributions when a minimal amount of fines generation is desired. All of these hammer types have wear-protected tipping added to prolong wear life. The Mikro-Pulverizer is an economical and effective size reduction system for a variety of materials. The Mikro-Pulverizer can provide top size control down in the range of 50 microns, and with a change in operating parameters and screen sizes, many other particle sizes can be achieved, as seen on this slide. As an example, the combination of higher rotor speeds, smaller screen openings, and the maximum surface area of the grinding elements leads to the production of the finest end products. The utilization of lower rotor speeds, larger screen openings, and grinding elements with minimal surface area produce the coarsest end products. Variations of these operating parameters and alternate internal machine components allow for a wide application range for this type of mill. Since hammer mills will generate airflow, the air generated during the milling process has to be vented from the machine. The most basic and compact Mikro-Pulverizer system operation is shown on this slide. The mill and product collector are mounted on a hopper. Material is processed in the mill and displaced air and product mixture flows to the product collector. Particles entrained in the airstream are collected in the filter and discharged back into the hopper below. For continuous operation of the Mikro-Pulverizer, material can be air conveyed away from the mill and collected in the downstream product collector as shown here. The valve you see located in the ductwork at the inlet of the conveying duct under the mill is used to regulate the amount of air pulled through the mill. The next topic will be size reduction using pin mills. Hosokawa manufactures both the Alpine UPZ and the Mikro UMP pin mill product line. The Alpine UPZ and the Mikro UMP pin mills are used for a variety of applications where medium to fine size reduction is required. These pin mills provide for an end product with a low amount of fines and good flow properties. Materials that are sticky and tend to plug hammer mill screens work well in pin mills, as there is no screen that provides retention of the material within the mill. Particle size in a pin mill is controlled by the variables of rotor speed, feed rate, and airflow. By utilizing a higher rotor speed than the Mikro-Pulverizer, the pin mill can produce even finer products. Our most common pin mill design is the single rotating pin disc design with stationary door disc and narrow grinding chamber. Centrifugal forces generated by the rotating disc causes the material to radially pass through a labyrinth of pins aligned in circular rows. Material is reduced in size by impact as it passes through the rows of pins. A bottom outlet is used when material is gravity discharged from the mill as shown above, and a tangential outlet is used when the material is air conveyed away from the mill. The tangential outlet design is also shown on this slide. No screens are used in pin mills to control particle top size. The high speed of the pin disc generates the finer particles. Tip speeds in these pin mills can reach up to 150 meters per second. The overall particle size distribution generated in these pin mills is much wider than the hammer and screen mill due to the lack of a screen for top size control. Our pin mills can also be designed with counter-rotating discs. Due to the very high differential tip speeds in these mills of up to 200 meters per second, they can produce even finer grinds than the single rotating pin disc design. For special applications, a wide chamber design is used to process sticky materials. The wide chamber helps to eliminate any material from accumulation within the mill. With a pin mill, the particle size is controlled by three parameters: feed rate, rotor speed, and airflow. Varying these parameters will have the following effects. Increasing the feed rate will result in a coarser particle size, while reducing the feed rate will have the opposite effect. Increasing the rotor speed and impact force will generate a finer particle size, while reducing the speed will also have an opposite effect. And lastly, increased airflow will produce a coarser product, while decreased airflow will produce a finer product. For pin mills with a single rotating disc, this slide shows common results for a variety of fine chemicals. Here you can see that we can achieve particle sizes in the range of 100 microns down to less than 40 microns on a variety of fine materials. Wide chamber pin mills are good for processing sticky materials. As an example, various spices with high oil content or fat content can be processed without the need for cooling. Under chilled or cryogenic processing, much finer particle sizes can be achieved. Hosokawa manufactures a wide range of pin mills from the smallest 33 mm diameter unit up to a 1.4 meter diameter model. Units are available in all materials of construction and finishes. Design pressures of the units range from atmospheric to 10 bar overpressure. Pin mill systems also require additional ancillary components to allow them to function properly and efficiently. Shown above is a gravity system. Depending on the air volume generated by the mill, the system can be used with or without induced air conveying as required. This is a once-through negative pressure system and is widely used when continuous operation is desired. This basic system with some additional ducting, a heat exchanger, and some additional instrumentation can also be operated as a closed-loop system. Closed-loop systems are especially desirable when processing with an inert gas, as in the case of processing a material that may be a potential explosion hazard. Closed-loop systems are also used when cooling of the processed gas is required, or when heat recovery for energy efficiency is desired. Next, we'll look at the Micro ACM air classifier mill, its design, its operation, and its application. Air classifier mill is a general term used for many types of impact mills that also incorporate dynamic air classifier technology as part of the mill design. The Micro ACM was developed by Hosokawa to address the need for finer materials and to provide the user with much more flexibility and control when there was a requirement for producing different products. Air classifying mills are the most widely used milling technology in the powder processing industry today for the general size reduction of fine chemicals and food products. The basic advantage of these mills is that they grind and classify in one step. In the air classifier mill, particle size is easily controlled by adjusting the speed of an internal classifier wheel. Here you can see the classifier wheel mounted in the mill housing. You can also see the shroud and baffle assembly that separates the classification zone within the mill from the grinding zone. In this cross-section of the Micro ACM, you can see the path of material and air within the mill. The air path is shown in red, and the material path is shown in blue. The main principle of this mill type is to use air to convey material to the mill, air to classify the product into fine and coarse fractions, and air to convey the fines out of the mill. Coarse material is then returned to the grinding chamber for further size reduction. This process is repeated on a continuous basis. Let's look in more detail how air and material flows through the mill. The main airflow is introduced to the mill from underneath the main rotor disc as shown here. Air flows from the mill inlet and enters the grinding chamber from underneath the main rotor via an elutriation ring that evenly distributes the air around the circumference of the impact rotor. Material is introduced radially into the grinding zone at the hammer tip, where it is impacted by rotating hammers as shown here. Processed material is then carried by the airstream over the shroud and baffle to the classification zone shown here on the left. Correctly sized material passes through the classifier and exits the mill through the upper volute assembly as shown on the right. Oversized material is rejected by the classifier and is carried back by the air to the grinding zone by passing underneath the bottom of the shroud. Air classifier mills can be used for a variety of applications. Due to the requirement for air for processing, heat-sensitive materials can be easily processed. The makeup air to the mill can also be conditioned so that humidity and temperature can be controlled when processing hygroscopic or heat-sensitive materials. Heat can also be added to provide drying when low levels of moisture need to be removed from the product. A variety of designs and sizes are available. Small units of 1 horsepower are capable of handling a few kilograms of material. Sanitary designs are available for handling pharmaceutical and food-grade products and when special cleaning and sanitary requirements need to be addressed. Large capacity mills of 600 horsepower and more are designed with special wear-protected internal components. These mills are available for minerals-related applications or materials that are somewhat abrasive in nature. For handling materials that present an explosion potential, these mills can be designed to handle an overpressure of 150 psi. While the classifier speed has a large effect on particle size, airflow can also be adjusted to change particle size. While the primary purpose of the classifier is to control particle top size, the mill internal components can also be changed to adjust the particle size distribution. As an example, the standard liner configuration supplied with these mill types is the multiple deflector liner. The liner type has vertical grooves designed into the circumference of the liner. This type of liner serves the purpose of slowing the circumferential speed of the particles and deflecting them back into the path of the rotating hammer, maximizing the impact force of the particle. The liner type can also be changed to reduce the generation of fines or to make an overall coarser size distribution. The use of smooth liners in the grinding chamber will decrease the impact force of the hammer to the particle. The impact hammer design will also affect the impact force and thus affect the end product size. An alternate type of impact hammer is the pin. Use of a pin rotor reduces the impact force, providing a coarser grind and minimizing the generation of fines. The rotor speed can also be reduced to minimize the impact force and to reduce the generation of fine material. Adjustment of airflow and classifier speed allows for the attainment of many different particle sizes. Here are examples of particle sizes that can be achieved with the ACM on a variety of different materials. Here you see a coaxial ACM design with a vertical outlet conveying milled material directly to a process receiver. The main air supply to the mill is split into 2 lines to allow for the pneumatic conveying of the feed material to the mill feed inlet. In this system, a volumetric screw feeder is used to gravity discharge feed material into the pneumatic conveying line to the mill at a specific rate in order to utilize the full horsepower of the impact rotor. Here we've added an inline classifier for the purpose of making both a top and bottom cut in one pass. Here the mill defines the product top size or coarse end of the particle size distribution, and the inline classifier removes the fines fraction, producing a very narrow particle size distribution. This system is also designed to handle materials which present a potential explosion hazard. The valves shown here in red at the air inlet and discharge of the system provide isolation and containment of the overpressure and exhaust in the event of an explosion within the system. The valves will close under flow and pressure and will contain the explosion. Number 4 on our list is the Alpine AFG Fluidized Bed Jet Mill. Moving on to the requirement for the production of finer materials, we come to the discussion of the Alpine AFG Jet Mill. This fluidized bed jet mill uses particle-to-particle impact as the mechanism for size reduction. High-pressure compressed gas is used to accelerate the particles to a central focal point within the bed of material where impact and size reduction take place. These types of jet mills also use dynamic air classifiers to control particle top size. The AFG jet mill design incorporates a grinding zone as shown here at the bottom of the mill. The classification zone is located in the top section of the mill. Feed material is introduced to the mill through a top gravity feed inlet as shown here. These mills work by accelerating gas through a nozzle directed to a central focal point. Multiple nozzles are used to generate a grinding zone at the center of the mill. The material bed height in these mills will completely cover the nozzles during operation. Only gas and not product passes through the nozzles. The high velocity gas entrains the material in the bed, and the combined gas material mixture is directed to the central grinding zone. Particle-to-particle collision is responsible for size reduction. Fine material is carried by the upward flow of air to the classifier wheel, where material ground fine enough exits the mill and oversized material returns by gravity to the bed. All AFG mill designs incorporate a radial nozzle arrangement, with the number of nozzles used varying with mill size. In general, the larger the mill, the higher the quantity of nozzles utilized in order to introduce the correct volume of air required for grinding. Different types of nozzles are also available depending upon the requirement of the application. Designs are available for handling materials that are potential explosion hazards. Due to the high volumes of gas utilized in processing, in most cases it is not economical to process materials using inert gas. For materials that are potential explosion hazards, the mills can be designed for high overpressures, effectively containing any explosion that might occur. For the processing of extremely abrasive materials, these mills can be lined with ceramics or polyurethane. New technology allows for the high wear components, particularly the classifier, to be made in silicon carbide or a completely cast aluminum oxide wheel, providing thousands of hours of service life when processing abrasive materials. This chart will help you better understand the basic operating variables of a fluidized bed jet mill and how they affect end product fineness. Just as in a micro ACM, the classifier in the AFG jet mill is used to change particle size. However, there are other options to achieve a desired particle size when more than classifier speed is required. For example, while maintaining grind air pressure and classifier speed, the use of smaller diameter grinding nozzles will produce a finer product. Please take some time to come back later and review these operating parameters and how they affect particle size. The AFG jet mill can handle a wide application range. Due to its operating principle, it can handle extremely abrasive materials, as particles are impacted against each other and not against the internal components of the mill. Very heat-sensitive materials can also be processed. Due to the rapid cooling of the grinding air as it expands in the grinding chamber, the mill operates at reduced temperatures. Soft and sticky material can be processed as buildup is eliminated due to the particle-to-particle impact and not particle-to-hammer or mill wall impact. Materials requiring a high degree of brightness or purity can be processed in these mills, as most contact with ferrous components is eliminated, or ceramic components can be used to minimize ferrous contamination altogether. This is a flow diagram depicting an AFG fluidized bed jet mill installation and the system components that are required. In the design of the AFG jet mill system, the mill typically will operate either zero or slightly negative pressure in the grinding chamber. The system fan is sized to maintain this pressure, and a pressure transmitter located in the grinding chamber senses the chamber pressure and provides feedback to the system fan in order to maintain a constant mill pressure and airflow. Consistent airflow is important on all the systems we have shown in order to maintain a consistent quality product. Our last subject is the Alpine Super Orion ball mill. Over time, our superfine ball mill and classifying systems have been improved and are now capable of achieving much finer products. In the past, a particle size with a D97 of 10 microns was only possible. We can now achieve products with particle sizes down to a D97 of less than 3.5 microns, with a D50 in the range of 1.5 microns. This improved performance is made possible by the optimization of all ball mill system parameters, including the incorporation of high-performance classifier, the use of improved control systems, and the use of grinding aids. There are quite a number of processing parameters which influence the performance and efficiency of a ball mill classifying system. Let's look at them briefly. Ball mill speed. Speed can be varied by use of a frequency converter to optimize mill performance. The length to diameter ratio of the drum. A longer drum will lead to a product with a higher fines content. Selection of grinding media. Some options include silpebs or balls in steel or ceramic. As an example, silpebs have a higher bulk density and provide for more efficient grinding in some cases. Sizing of the grinding media. The proper sizing of balls or silpebs depends upon the end product fineness and also the feed size. Selection of the mill lining. For soft minerals, usually steel linings are used, sometimes with a high chromium content option, which reduces material discoloration. In some cases, a ceramic lining is used if the highest whiteness or brightness is needed or any iron contamination must be eliminated. The mill discharge system can be air-swept, overflow, or slot wall design. Air-swept mills are mainly used for coarse materials and are not suitable for fine grinding as too much coarse powder is carried out of the mill by the airflow. A slot wall is the best option, as very fine grinding media can be used, which is easily retained within the mill. On top you see a single chamber ball mill with a peripheral outlet slots, which can be used for standard and ultrafine materials with a D97 of between 15 to 100 microns. On the right are shown some examples of grinding media, silpebs and balls made from steel or aluminum oxide. The illustrations on the left show the flow patterns of the media within the mill. Figure A shows a cascade motion where the media is mainly rolling and we generate shear forces for grinding. When you increase the speed of the mill as shown in Figure B, a cataract motion is generated where we develop impact forces as the media is lifted up and falls back onto the media product bed. The ideal condition is to operate at the transition point between these two flow patterns in the mill in order to utilize both effects. This condition is reached at about 60 to 80% of the critical speed of the mill, which results in the flow pattern we see in Figure C, where the centrifugal force is high enough to prevent the media from completely falling back down onto the material bed. A high-performance classifier in the system circuit is a requirement for producing these superfine products. These classifiers are capable of achieving the finest cut points, very sharp top cuts, excellent fine yields, and the highest possible capacities with excellent wear protection. The Alpine Super Orion ball mill in particular is used for processing industrial minerals. What are industrial minerals and fillers? Industrial minerals are geological materials which are mined for their commercial value. They are used either in their natural state or after some beneficiation. Industrial mineral fillers are a variety of processed industrial minerals that may be irregular, fibrous, or platy in shape, and which are typically used in large volumes in paper, plastic, paint, and rubber products. Standard products are in the range of 20 to 100 microns, which is relatively coarse when considering the capabilities of these ball mill systems. The requirement now is generally for finer grades of materials, which we define as ultrafine products, which are in the range of 5 to 20 microns. Even finer grades of materials are now required, and we define these as superfine products with a particle size of less than 5 microns. Super Orion ball mill systems are also used to process hard minerals. Because of the hardness of the material, a higher specific grinding energy per ton of material is required to achieve the same particle size as a soft mineral. Also, wear on the system components is much more severe and requires the use of affordable, long-lasting, replaceable components. Here we show examples of typical hard minerals and their uses. As our standard of living continues to rise and all related products become more advanced, high-quality standards for ceramic tiles, sanitary ware, porcelain, and special glass are required. The requirement for these mineral powders becomes more stringent in terms of top size, particle size distribution, and purity. This is a PLC screenshot of a closed-loop ball mill classifier circuit with the ball mill positioned on load cells for weighing the total mill content of media and material. Incorporation of load cells represents the latest technology for controlling the feed rate into the ball mill. By controlling the mill weight, the optimal amount of material is always in the mill bed, and the milling efficiency is optimized by never over or underfilling the mill. The classifying air volume is measured and kept constant by use of a thermal mass flow meter and control device in order to assure consistent product quality. This flow diagram shows a ball mill with a 450 kilowatt drive and a 500 ATP multi-wheel classifier. At a D97 of 10 microns, this system can produce 5 tons of material an hour. This system can also produce a finished product with a D97 of 3 microns at a capacity of 1.2 tons per hour. This demonstrates that superfine grinding on ball mills is possible. There are hundreds of size reduction technologies available from many suppliers around the world. Hosokawa manufactures many different milling systems. Some are multifunctional and can process a wide variety of materials like the Mikro-Pulverizer hammer and screen mill. Others are more specialized, like the Micro-Atomizer for PVC or the Micro EACM for carbon black. With all these options, we felt this presentation would be helpful to learn a little about some of the milling systems we produce that address the widest range of materials and the widest range of particle size and capacity. Today we briefly discussed these 5 milling technologies. We reviewed their design, how they operate, the wide range of options available, and some common applications and system designs. If you would like to learn more about one of these technologies, please let us know. Our follow-up email will include important links to additional informational resources, including demonstration videos, other educational webinars, and product brochures. This concludes my presentation today. I hope you found the information useful and informative. If you would like to contact me later, please feel free to do so. My contact information is listed here. Thank you for your participation.